So what's this? Ti minus 1 Ti and Xi and the eta I 节 are points in the subinterval Ti minus 1 Ti. So their difference will not greater than the oscillation of the function in the interval. Are denoted by omega. Where omega ij? What's omega ij? Omega ij is the supplement of st in the Ti minus 1 Ti interval. The jth component okay, this is the oscillation of this function on the interval Ti minus 1 Ti, right? Omega ij. So denoting such omega ij to be this quantity, this estimate can go further to get the final result here. Okay, now with substituting, of course this is also true by taking absolute value of everything. The argument goes still true. Okay, so substituting this computation, this estimate, to our previous result here, to the previous estimate of the range of inscribed polygonal of gamma under the with respect to the partition P, we obtained substituting here precisely here. Okay, we get have a look clear. The absolute value of the term in the summation has been estimated in our this page argument. So using this result, we get L gamma P subtract A B gamma dot maybe T. This will not greater than I from 1 to m. I from 1 to m, and then the summation term has been estimated by sigma omega ij Ti minus Tj. J from 1 omega ij Ti minus Tj. Then this we can switch the order of summation. Switch the order of summation. That is the oscillating area with respect to the partition. Okay, so this part, for defining integral, we have upper sum and the lower sum. Their difference is the oscillation area Okay, so since the gamma j for every j is integrable, because the derivative is continuous functions are integrable on the interval AB. There is a delta positive if the partition P is less than delta. Then the oscillation area of this function with respect to the partition P will not greater than epsilon for the epsilon we take at the very beginning. Therefore, for this delta, if our partition P is final enough, every term in this final summation will not greater than delta. So this will less than n epsilon. That is to say, for any epsilon positive, we can find a delta positive. As long as the gap of the partition is less than delta, then the length of the resulting inscribed polygonal, the absolute value of the difference of the term of the length of the inscribed polygonal which the integral absolute value is less than a constant multiplied this epsilon. That is to say, the difference of the length of the inscribed polygonal can be very, very close to the integral of the norm of gamma dot. So this proves that gamma has length. Just the length is just this integral. So this proves our result that L gamma is the integral. Okay. Now, for piecewise smooth curve, our previous result we just the lemma we just proved is for C1 curve. This is not only a smooth parametric curve. This is in fact more because it is also differentiable at the endpoint. In our proof, we need this, but I have no time to point out where we use this point. Okay. So that is for smooth curve. So for piecewise smooth path, can we have the same result? This is the theorem. A piecewise smooth path C is rectifiable, and the length is the integral of this. Here gamma is any of its parametrization. Okay. So we prove this. So this is a piecewise smooth path. Maybe I will use so this is a piecewise smooth path. Okay. We first remark that our previous lemma still true for smooth path. Not only C1. No. We don't need to assume C1, although our proof is for C1. But for smooth path, that is the the gamma is not differentiable at AB, the result is still true. Why this is true? So we give an intuitive explanation. This is A, this is B. So we say that L gamma, no, our notation is L gamma is AB for C1. Right? We have this result, or we just prove this result. Now, if gamma is only a smooth patch, that is, gamma might not differentiable at AB. Gamma might not be differentiable at AB. How to prove this? Now, we take we restrict our gamma to a sub-interval determined by alpha beta. So for the restriction of gamma to the interval, gamma restrict to alpha beta, it is C1. C1 and the smooth parametrization only difference by the differentiability of the endpoint AB. C1 means it is also differentiable at AB, but our smooth parametrization does not require the gamma to be differentiable at AB. Now I remove AB, then the two concepts are coincide. Okay, so the smooth parametrization curve, parametric curve on AB restrict to alpha beta is a C1 curve in AB. C1 curve defined in AB. Therefore, by the result, we see that the restriction curve gamma tilde, the length of the restrict curve is AB. Gamma tilde is precisely gamma, but the alpha beta. Okay, now we let AB goes to alpha goes to A, beta goes to B. Then or in other words, if alpha and beta are very close to AB respectively, then this will very close to the range of gamma, and this integral will very close to the integral in the interval AB. So using this idea, we can extend our lemma on C1 curve to smooth parametric curve. Okay, this is the first step to prove our theorem. Firstly, extending the previous result from C1 to smooth parametric curve. Then, for the piecewise smooth curve, piecewise smooth curve just the union of smooth curve. For each smooth curve, this formula is true, as I explained here. Therefore, for the union of a smooth curve, that is piecewise smooth curve, for each such a portion of the curve, the result is also true. The range of each Ci is also an integral. Okay. Therefore, the range of each part, as we proved in the previous lemma, the range of the union of two piecewise smooth curve, or finitely many piecewise smooth curve, once they have common endpoint, so that they can be joined together, the range of the resulting curve is the sum of every curve, but every curve is the integral. Therefore, we will conclude that the range of the curve is the total integral. Okay, or we can write this more explicitly. C is the union of C1. C1 defined by the A1, A2. Sorry, maybe I will use the very organized notation. Ci is gamma I from AI minus 1 AI. We can assume that the domain of definition of the smooth portion, say smooth. So piecewise smooth C is the union of finitely many smooth curve, and each smooth curve Ci has a smooth parametrization. Okay, we might assume that the domain of definition of the gamma I is the AI minus 1 AI. Therefore, the gamma T, the parametrization of say gamma T is gamma I T for T in the interval AI minus 1 AI. And the gamma is defined A0 to AK. Sorry. This is the parametrization of C. So since gamma I are smooth, so Ci has range. Therefore, C is also rectifiable. Okay, and the LC is the sum of LCK, but the sum of LCK is the integral of AI minus 1. The sum of LCI, not CK. K is the total. Okay, so this is AI gamma I dot dt. But in the interval, gamma I is gamma. Therefore, this can be written as I equal to 1, AI minus 1 AI gamma t dt. Because in this interval, AI minus 1 AI, okay, gamma is gamma I. So this is the A0 to AK. So this proves the theorem. Okay.